This lesson discusses a set of use cases in the artificial intelligence area, deep learning, social networks. Very hot fields with really exciting applications, which have really been shown clearly to have big impact. The first is the large-scale deep learning example. This is uses so-called learning neural nets, which involve large numbers, billions of links between neurons, and they are designed so that when information is fed in the case of the diagram at the bottom where it says in, then out pops at the top neuron an answer, which is a classification. So neural nets are classifiers, and they're used in the examples discussed here. Um, they're used to do car driving, face recognition, language processing, by being able to classify the noises or whatever you want to say, the audio signals produced when people speak. That's for the last case. So you do that by having typically either um, supervised or unsupervised cases. Supervised is probably the more typical case where you have a whole set of data. In the case of faces or car driving, it's image data, images of faces or images from the webcam at the front of your car, monitoring what your car is seeing. And then you need to either classify the face or classify what the car should do. In the case of the language processing, classify the signal as to what its implication is. These are hugely computationally intense because, I say, like this particular application described here, the face recognition had 11 billion parameters. It was implemented with 10 million images on a 64 GPU HPC cluster. It did not use clouds because it used MPI with low latency, high performance communication. So this was not a huge database, but they point out that 100 terabytes or more might be involved in some of the cases like the car driving, which is 100 million pixels, 100 million images. So another image. These are all image cases, these particular cases here. What you feed in at the bottom are the pixels for each image. So you feed in a whole set of images, and then there's some very clever optimization algorithms that are used to train the networks. This is one of these ego projects where you're taking where the world you're taking is the set of images, and the parameters you're optimizing are the weights of these links called W1 and W2 in this diagram here, W2, W1. These are the weights. There's one for each link, and there are lots of links here. And one has to run this many times, iterate it, to get to converge to a good classification. This particular group uses Python to do the rapid prototyping, to experiment with different approaches. Here's an application from David Crandall, an Indiana University faculty member. And he's looking at the plethora of images that we get from the web. And one of his ideas is to be able to automate the relative location of images by effectively doing a fit of the scene implied by these images. So if you take an image, then if you assume it was taken from a camera in a particular position, in a particular orientation, then you should be able to align the images taken by these cameras so that they correspond to the same three-dimensional scene. So the idea is to reconstruct the scene, such as the Eiffel Tower or something like that, and the images, so that you can produce a very nice way of browsing the images, and also a nice way of finding automatically three-dimensional images from multiple two-dimensional images. That's actually sometimes done by properly located cameras and actually doing the construction automatically. This here, the idea is you don't even know that information. You may know nothing about the images, but you're just trying to optimize them just by the overlap between the um, objects recorded by the pixels. And he is using Hadoop, and of course, this is potentially a huge problem with, as we keep saying, 500 billion images on Facebook and 500 million added to social media sites every day. Here's a picture of this trying to represent it. We have a collection of pictures, and then they reconstruct this three-dimensional view here, and they are all, each of them is placed in the location they are with that camera. So this is a pretty nifty, exciting application. Has other natural, large-scale, ego-like things. This is clearly exascale global optimization in this sort of crude, in this very direct fashion, and it is quite promising that this type of, this is a good example of what the world's data explosion can enable. Here's another application from Indiana University, Truthi, which is studying information diffusion. We actually discussed information diffusion earlier in the healthcare area by noting that the same technology used to model epidemics could also model not just the movement of the viruses and bacteria from the epidemics, it could also model any information. Some scandal about a celebrity or news about an earthquake, that the diffusion of information can be studied from Twitter data. And this is a research project trying to understand this movement and what it implies. Also could be applied to sort of detecting unharmful information at an early stage, and so on. And Twitter actually gives away fractions of its data in with different costs according to how much of that data you get. These people are looking at 30 terabytes a year, and they're using NoSQL technology, HBase with an indexing capability built on HDFS as the backend storage, and in-memory databases. The idea is to be able to query this data, look for anomalies, clustering of topics, classifying the signals, and looking at the implications for this spread of information. The actual data analysis is again used in Python. Uses Python today. There's an increasing trend to use Python as one's data analysis engine. Cloud sourcing has been known for some time. Amazon had something called the Mechanical Turk, which is one of the earliest cases where cloud sourcing was introduced. And in the humanities, it's a particularly valuable way of doing things because it's effectively a generalization of the surveys that an ethnography that dominates is an important way of gathering information in that field. This particular use case suggests this field has only really been just started and the surface is scratched, and it's possible to do a lot better than we're doing up to now. And there are obviously important issues for privacy when you have individuals involved, and how much anonymization is possible is not clear. They claim that they might get hundreds of terabytes of data, especially with the multimedia type information. This is a network science resource called SciNet, headed at Virginia Tech. And it's basically a database holding graph information and other types of population data, and a compute resource and a set of analysis tools which basically allow you to analyze this data and do your research. So it's expected to allow to grow in size. It's already been used in classes, and it's looking how to actually use clouds to provide a more flexible, elastic resource. Because at the moment, if it gets too many users, then it just runs out of space. So clouds are a natural, elastic clouds are a natural approach to this problem. So this is one of the most modern and up-to-date and comprehensive network resources to allow you to do this research. Note that when you have a particular field, you can distribute the capabilities of software which you download, or you can actually have a back-end cloud, which is a resource where you can run the software by uploading your data. Here's an interesting example from NIST. NIST is known for its very important base data sets, which have been used to benchmark and quantify the capabilities of different areas of analytics. So it's speech and language processing, video and multimedia processing, image processing, and other types of heterogeneous data processing. And their data sets are used as the industry, inverted commas, industry standards to try to understand how good your particular new nifty analytics. As you go to the NIST website, use their standardized benchmark set and measure the performance of your new algorithm. So they point out that you can either do this at the level of the data or the level of the algorithms, and by having a standard harness which allows the algorithms to be placed, say, on a cloud, and then this would provide a cloud to do this testing. So we have around 30 terabytes of storage, 900 million web pages, 100 million tweets, 100 million images, and video clips, hundreds of thousands of video clips, and other smaller data sets. So this is obviously an important national resource, and we need to, I guess NIST and the nation need to decide how best to host that data and make it available for richer and richer sets of experimentations. And clouds are obviously, clearly, the right approach to this. This introduces machine learning, because it is the classic place where machine learning is tested. As I said, machine learning is actually implied in lots of the previous use cases. They may not use the language machine learning, but they are using machine learning. Deep learning is directly machine learning. It's an example of machine learning. But all those ones which had ego were effectively using machine learning tools. But of course, this particular data set explores many different machine learning algorithms. When we look at the classification, we would define machine learning into two types: local machine learning, where the machine learning is applied to every individual item in the data. Like if you have a set of images, the machine learning is applied to each image. Alternatively, there could be global machine learning, as in the case where the images are being classified together, in the case of that internet image grouping for three-dimensional views, where clearly that was a global machine learning algorithm across all items of the data. And of course, the deep learning is an example of global machine learning.